Okay. Hi guys, I'm Katie Driscoll, and I'm talking about the last stage of the scintillating tile stuff. I promised in the last one. But this is the design and assembly of a Faraday dark box for the characterization of the scintillating tiles. So Alyssa and Lily already talked about this, but our lab is a part of the EPIC collaboration, working on the electron ion collider, and we specifically were working on the subdetector of the LFH cal, which involves the scintillating tiles. So we have all of these little tiles. We need to make sure that they're all identical. And so Lily talked about her translation stage and how it will be like an automated platform that can transport the tiles for testing. So the main question that I was trying to answer was, where do we do all this? And that would be in the dark box, as Lily mentioned. So this box has a couple of key parameters. It has to be light tight because the slip-ons, they read photons, so we don't want any external photons getting in the way of our measurements. The box also should be a Faraday cage, so it should be completely conductive such that there's no electromagnetic radiation inside, because that can interfere with the slip-on's ability to read data. And then it also has to be large enough to contain the translation stage, but also have space to do the tile testing. It has to be easily accessible so that we can open and close it and access the inside. And we also need to have a way to feed in wirings and other connectors that we might have. So how do you build a dark box? The first step was to design it. A couple questions that we were just keeping in the back of our mind while we were designing this was, what were the dimensions going to be? The space we had allowed us for the box to be 4 feet long, 2 feet wide, and 3 feet tall. And then just kind of thinking about, how do you keep it light tight? What's the best way to access the inside? What type of doors would we want? And then what materials will we need? So to figure out our materials, first step was to hop on McMaster-Carr. This website is great if you're ever trying to build anything. It has a super big collection of materials. And from that, we decided that we would make our box out of 80-20s. These are like aluminum beams that have these slots in them, which makes them super convenient to build things out of. So this would definitely be the best material to make our box from. So I hopped on Autodesk and created this design for the box. You can see that we went with like a double door design because this box is just so long. And then we also found some cool different things to use with the 80-20s, like these 3-way corner brackets. They would make putting the 80-20s together at junctions super easy to make perfect 90-degree angles. And then we also found these flat 80-20s where they have this side that's like completely flat. And we use these for the doors because when we're closing the doors, we want to make sure that they're completely flush so that they're light tight. And this flat side looks perfect for that. So after that, with the Autodesk, we knew what all the parts we needed to buy. I will not say how expensive they were. And then we ordered them and started the next phase, which was preparation. So we had all these materials, they all needed to be precise sizes. So our motto for this was measure twice, cut once. We don't want to make any mistakes. So we trimmed all of our 80-20s to be the size that we wanted. We had to shear all of the sheet metal, which was going to be used for the walls. We also had to tap the ends of a lot of the 80-20s using this tool, which kind of like makes your own threads so that you can screw things into the ends. And then we also had to punch holes in the sheet metal because we're going to be bolting this onto the outside of the 80-20s. So we needed to mark and align a bunch of holes and punch them out so that we would have a space to do that. And then we also had these side panels that were going to feed through wires and connectors, as I mentioned before. So we used the water jet to make these cutouts in the sidewalls of the sheet metal. And then we used the laser cutter to cut out the holes we needed in these black acrylic panels, which are going to be kind of like attached as like patches to these sheets. yeah, so now everything is prepped, so it was time to assemble the box. This is just gonna be like a montage of pictures of us putting it together. Shout out to Alyssa, Lily, and Daniel for helping do this. This was like a lot of work. But here's us putting together the 80-20 frame. Great thing is we had all the pieces cut to how we wanted, and with the Autodesk design, we knew exactly how everything was supposed to fit together. So it made this process largely straightforward. Then we attached the sheet metal. This was not as straightforward. The interesting thing with sheet metal is that usually when you're working with 80-20s, you would just kind of slide on the nut and the bolt through the slot. But since we had the frame already built and you can't really just slide on a whole piece of sheet metal, we had to get these special spring-loaded nuts, which have this like little ball with a spring in it so that you can insert it into the slot without having to slide it on. And that made the process of putting the sheet metal on much easier. Just put the nuts in, align it with the holes that we had punched, and bolt everything down. Then we had to fasten the doors. This proved to be more challenging than we expected, because we have these 80-20s on the top and the bottom that hold the latches that we used. So when we tried to close the doors, they would actually hit the 80-20s and they wouldn't close. So Alyssa spent 2 hours filing the sides of an 80-20 so that we could make a little gap for the doors to close. But her hard work paid off and we got them to close successfully. And then final finishing touches on the box. We aluminum taped all the sides to make sure that there were absolutely no light leaks. We attached the acrylic panels to the outsides, and then we added this foam seal to the doors made of RF shielding. And it basically fills in any gaps that there might be when we close the door. And the flat 80-20s that we used for the doors were super helpful with this because it created a flat edge for the foam to adhere to. So yeah, here's the finished product. If you're wondering how big this box is, it is quite large. I fit comfortably in like half of it. So yeah, it's a big box. And like Lily said, we tested to see if it was a Faraday cage by putting her phone inside, closing the box, and I tried to call her and the call would not go through. So we succeeded in blocking out all the EM waves from the inside and made a Faraday cage. And then we put in her translation stage in the box. You can see that it fits like very nicely on the right side, but leaves plenty of room on the left to do the testing of the tiles. So that was great. So what are the next steps? We're going to do some LED testing with the SIPMs, like Rose said, to really confirm that it is light tight. And then we'll continue with the suction cup setup for characterizing the tiles with the translation stage inside the box. So yeah, thank you for listening. I hope you enjoyed.